Hello everybody, my name is Liam Lynch. I am a graduating senior majoring in biochemistry and Spanish, and I am presenting my honors research for Drury University for the semester of spring 2022. The title of my project is The Effects of Plumbagan Analogs on the JAK-STAT Pathway. My directing faculty is Dr. Mampati, and my honors director is Dr. Sher, and my motivation behind this project was to explore the field of medicinal chemistry in a novel and meaningful way. One way of doing this was by performing research on a stock of anti-cancer analogs previously synthesized by Dr. Mampati's lab, and these analogs are derived from the anti-cancer molecule plumbagan. So the problem. So this is plumbagan and its structure. It is a 1,4-naphthoquinone and it is derived from the plant plumbago. It's a proven anti-cancer compound that exerts its effects on numerous pathways in numerous cell lines. And some of the cancers that plumbagan has been proven to inhibit include breast cancer, lung cancer, and leukemia, just to name a few. However, many efforts to include plumbagan into modern cancer treatments have failed, and this is because plumbagan itself has a poor bioavailability. When administered intravenously, it fails to selectively target tumor growth. And so the goal of our research is to target this problem, the poor bioavailability. The intention behind analyzing analogs of plumbagan is so that these might show the same promising anti-cancer effects while making up for plumbagan's poor bioavailability. We'll test this by comparing their effects on the JAK-STAT pathway. So plumbagan is a known inhibitor of this pathway, and thus we can test the inhibition of our analogs to that of plumbagan on U266 cells. But what is this pathway anyway? Well, the JAK-STAT pathway is a regulatory pathway. In healthy cells, JAK activates the STAT3 protein, which regulates cell development and stimulates cell proliferation. Cancer, if you can see where this is going, is the uncontrolled division of cells, which typically occurs when a mutation is present in the genes regulating, wait for it, cell growth and proliferation. Thus, in many forms of cancer, this pathway is somehow upregulated. One way this pathway is mediated is through interleukin-6. For our research, we chose the cell line U266 cells, or human beta lymphocytes from a patient with multiple myeloma, as it upregulates the concentration of interleukin-6, thus making this pathway upregulated as well. And this allowed for the inhibition of this pathway to be more observable. Plumbagan affects this pathway by inducing the expression of tyrosine kinase, SHP1. So as we can see here, SHP1 actually inhibits activation of the JAK protein and subsequent inactivation of STAT3. So we no longer see the activation from here that signals for cell growth and proliferation. So just to summarize, plumbagan causes more SHP1, which leads to more inhibition of the STAT3 pathway and ends up causing apoptosis. So for our research, we began by growing our U266 cell line. We used RPMI media and 15% FBS and 1% penicillin and streptomycin, and then we refreshed the media every 3 to 4 days by centrifuging the cells and putting in new media. Once we had enough cells, we could count them using a C-chip hemocytometer, and using this we could obtain a cell concentration of 2 million cells per milliliter. Then we plated 1 milliliter of cells with the compounds into wells. We incubated with DMSO as a negative control, plumbagan as a positive control, and the compounds all at a concentration of 25 micromolar. After incubating for 5 hours, the cells were removed and then lysed using repolysis buffer, sonicating 3 times at 0, 15, and 30 minutes for 10 seconds at a time. Then we centrifuged, and the cell lysate was collected in the supernatant to be used for STS-PAGE and Western blot. So, STS-PAGE is simply a method for separating proteins by their molecular weight. It utilizes sodium dodecyl sulfate, that's the SDS, to bind to proteins and give them a uniform negative charge. Then we use an electric current to pull this negative charge down the gel, and along with it come the proteins. The proteins with the least molecular weight move faster and appear towards the bottom of the gel, and our cell lysates were prepared in the gel as you can see here. We ordered them this way so that we could test different concentrations of antibodies in the Western blot, and we'll talk more about that soon. But first, the STS-PAGE was ran at 130 volts until the indicator was at the bottom of the gel, as you can see, and then we prepared the Western blot. So This involved transferring the proteins isolated from SDS page to a nitrocellulose membrane. We created a sandwich like here, which again utilizes a charge, allowing the proteins to be transferred to the membrane more easily. After 2 hours at 65 volts, the transfer was complete, and we could begin antibody treatment. And this is what the membrane looks like after being treated with PONCE-US. So we can see the lanes here, and we basically just use scissors to cut the membrane into strips for separate testing. But remember, we're looking for specifically the JAK2 protein. So this is why we began antibody treatment. We started by blocking the membrane with bovine serum albumin to prevent nonspecific interactions with random proteins and our JAK antibodies. And then after blocking, we incubated with primary phosphorylated JAK2 antibodies isolated from rabbit at 4 different concentrations. And these were 1 to 1,000, 1 to 5,000, 1 to 10,000, and 1 to 20,000, intended to bind to the JAK2 protein. We incubated overnight on a rocker at 4 degrees Celsius, and then we took it off and incubated it again with secondary phosphorylated JAK2 antibodies at a concentration of 1 to 5,000 for 3 hours, also on a rocker. And then finally, after all this, we used a colorimetric dye to visualize the plot. So the results are shown here, and basically what this means is that at the concentrations tested, DMSO did not show inhibition of the proteins between 100 to 150 kilodaltons, the rough weight of phosphorylated JAK proteins. Plumbagan did show inhibition here, and these were both expected as they were our controls. However, our tested compound, compound 11, did not. So, why might this be? Well, there are a few reasons. If we compare the structures, we see that both compound 11 and plumbagan are 1,4-naphthoquinones, which is because of these ketones right here. But the major difference is this big bulky structure on compound 11 at the second carbon. This structure greatly changes the molecular weight. It might obstruct the binding pocket, provide steric hindrance, or the presence of this nitrogen and extra aromatic ring could have varying interactions between the cell and between the compound and between the binding pockets. So we don't know. However, there are also other reasons that compound 11 did not show the same amount of inhibition. One of these other reasons is that the incubation time of our compound could have been just slightly different from the ideal incubation time of plumbagan. That and the concentration. Our concentration of compound 11 may be ideal at other concentrations, who knows. And overall, the rough conclusion, though, that we can draw from our research is that compound 11 at these parameters was not as potent at binding to the JAK-STAT, or not as potent at inhibiting the JAK-STAT pathway as plumbagan was. This conclusion shouldn't be determined as final, though, since compound 11 still needs to be tested at different incubations and concentrations. Still, this research has been greatly meaningful. Over the course of the research, we made several revisions to the procedure, optimizing it each successive attempt until we were able to obtain some fantastic results. The optimization of the procedure will carry on into summer research with my research buddy Zena and my amazing mentor, Dr. Mampati. And then just finally, I would like to thank Dr. Mampati and Dr. Schur and everyone else who has helped make this research possible.